Hi, my name's Steven, and I was working with Pranav on the M3 hackathon. So first, we're going to walk through our approach to predicting the housing prices in Ames, Iowa. So instead of focusing on the algorithm complexity, we structured this project around minimizing the generalization error. So the decisions we made from cleaning to ensembling was focused on the bias variance trade-off and validation evidence.
So now I'm going to talk about our objective and our evaluation metric. Basically, the objective was to predict the sale price variable using 79 explanatory variables. The evaluation metric is root mean squared error on the log transform target. RMSE penalizes large errors quadratically so that extreme mispredictions disproportionately increase loss. Because housing prices are right skewed, we took the logarithm of sale price instead of predicting raw dollar amounts in order to stabilize variance, reduce sensitivity to extreme luxury homes, and align training loss within our evaluation metric. This ensured that our optimization effective matched the scoring function. This basically means that like on a 50K error on a 200K house and a 50K error on a $1 million house is treated more fairly in that both are around 25% versus 5% errors in log space.
Next, I'm going to talk a little bit about data integrity and some of the missing values. So our first step was looking for and handling the missing values. So in this data set, there were a lot of NA values that represented some sort of structural absence, for example, no garage or no pool. Dropping these rows would introduce bias and reduce the sample size unnecessarily. So instead of doing this, we encoded the structural absence explicitly as none or zero. This preserved information while maintaining interpretability.
Now I'm going to talk about outlier analysis and influence control. So we started by identifying properties over 4,000 square feet and then sold them at that were sold at unusually low prices. These points exerted sort of a disproportionate influence on the regression slope estimates. These estimates are coefficient weights that multiply each feature in the regression equation. So this matters because if they're disproportionately influenced, then our regressor will be disproportionately influenced, and it might cause the model to overly favor the outliers. So rather than immediately deleting them, we first tested model performance with and without these observations, and we discovered that validation RMSE improved after removing them, which showed that they added some sort of noise. Because of this, we excluded them to improve generalization and stability.
So the most significant performance gains came from our feature engineering. So first we created total square footage by aggregating the basement, first floor, and second floor square footage. This reduced the amount of features that were wasting model capacity and better aligned with how buyers perceive the space. Second, we ordinally encoded quality-related features. So unlike one-hot encoding, ordinal encoding preserves the hierarchical structure. Basically, we converted categories into numbers that preserve the ranking, since the housing quality is not nominal and it has a ranking. Third, we introduced an interaction term, overall quality times the square footage, total square footage. This captured the nonlinear price acceleration in large, high-quality homes. We validated each of the features incrementally to ensure that it reduced validation error rather than inflating our training performance.
Finally, to discuss, sorry, not finally. We calculated skewness for all numeric features and applied log1p transformation to the ones that were heavily right skewed. Log1p means that we take the natural log of 1 plus the value, which allows us to keep zeros in the data. This sort of transformation shrinks very large values more than small ones, which reduces the influence of extreme observations and makes the distribution more balanced overall. As a result, our model became more stable and less sensitive to unusually large homes.
So our modeling strategy focused on balancing underfitting and overfitting. The tree-based models capture complex patterns, which help reduce underfitting, but they can become unstable if too flexible. So regularized linear models are more stable, but they may miss nonlinear structure. So instead of choosing one, we chose to blend them. Because their errors weren't identical, averaging their predictions reduces overall instability while keeping strong predictive power.
Now to discuss our validation framework, we started by using an 80-20 holdout split in order to evaluate generalization. We focus on monitoring the training RMSE, the validation RMSE, residual distribution, and error across the price range. The small gap between the training and validation error, as indicated in the learning curve graph, indicates that a stable generalization it exists and the model just works well on new data. If training error had been significantly lower than validation error, it would indicate that there was overfitting, and if both were high, it would suggest that there was underfitting. Neither of these occurred.
Next, I'm going to talk about some of our controlled experiments and what failed. So we intentionally stress tested our approach, and when we introduced high degree polynomial expansion like x squared or x cubed, training error dropped, but validation error increased, which is a red flag for overfitting. So when we one-hot encoded quality variables, which is where we converted the categorical data into a binary vector, it increased dimensionality. However, this change didn't really improve validation performance, which just means it added variance without bias reduction. These experiments reinforce the importance of disciplined feature selection.
Okay, so now I'm going to talk about model fit diagnosis. Based on the validation metrics and residual diagnostics, we found that errors were approximately centered and that no major uneven error variance pattern was observed. We also discovered that training and validation errors were closely aligned. These indicators suggest that the final ensemble that we created was pretty well fitted and that it doesn't memorize noise and isn't oversimplified.
Even though we saw strong validation performance, there were still some risks. So the holdout validation might underestimate variance compared to k-fold cross-validation. The interaction features increase model complexity and may amplify the overfitting if the dataset size were smaller. The model assumed future housing markets conditions resemble the historical data, which isn't necessarily true. And with additional time, we could implement repeated k-fold validation and Bayesian hyperparameter optimization to further confirm robustness.
So our final takeaways from this project is that it sort of reinforced some principles that we learned in class. So we learned that intentional feature engineering practices can reduce bias more effectively, and even more so than some aggressive hyperparameter tuning that we were trying to focus on earlier. We also learned that blending some complementary models can reduce variance when residuals are weakly correlated, and we learned that continuous validation is sometimes the most reliable method of generalization. And yeah, and ultimately we determined that model quality is not just about complexity, it's about error management and iterative testing.